Welcome you all to Principles of Organic Synthesis. So far we had 27 lectures where we studied aliphatic carbon-carbon, carbon-nitrogen bond formation, organometallic reagents, aromatic, electrophilic and nucleophilic substitution reactions, reactions of aromatic diazonium salts, then organophosphorus, sulfur, silicon, boron and tin reagents. Now we will start the free radical reactions. This is the last topic in this course. In this lecture we will study the principles of free radical formation, then the use of free radical reactions for the formation of carbon halogen and carbon carbon bonds. Now let us see the principles of the free radical formation. As all of you know very well, free radical is a reactive species and only few free radicals are known which are stable. Here an example shown. This is the first free radical. When you have this triphenyl methyl chloride, when you react with the silver, and this bond undergoes homolytic cleavage, and you will be able to form this triphenyl methyl radical. This radical in benzene solvent exists as dimer, as you can show here, and this is because this radical can undergo delocalization with the aromatic ring. In addition to that, is sterically hindered. Therefore, this radical does not undergo further reaction. It can be stable. It exists as a dimer, as you can see here. Now, the free radicals can be formed by three ways. The first one is if you have the weak bond. Let us take this compound. When you heat this compound, this bond is weak, it can undergo homolytic cleavage, you will be able to form the free radical which can lead further reaction. That means you can thermally cleave this bond homolytically, you can generate two free radical which can initiate the reaction. Similarly, you can also cleave the bond in the presence of light. When you apply energy, this also can undergo cleavage under irradiation. Then you will be able to form the radical which you can initiate the reaction. The other approach is redox reaction. You can provide an electron which can, for example, if you remember, for example, you take this ester, when you react with sodium, sodium can give one electron. When you give the electron, it can, already we have studied, once you form this radical which can undergo further reaction. So, radicals can be generated by three ways. If you have weak bond, this can be thermally, when you heat, it can be cleaved homolytically, you can form the radical. Similarly, if you can also irradiate, this bond can undergo cleavage and you will be able to form the radical. Similarly, you can also, if you provide electron, you will be able to form radical intermediate which can be further converted into useful compounds. Already if you try to remember, we have studied several radical reactions, and if you look at one of them, if it depends upon the nature of the substrates and it can undergo cleavage, and you will be able to form the radical which can initiate the reaction further. Basically, if you compare the organic transformations, if you form this radical now we have, for example, let us take HBr, it can abstract this hydrogen, then you will be able to form Br radical, you can get this product. So, hydrogen abstraction here takes place. And when you compare with the ionic pathway, and you can also, if you have anion, it can remove the proton and you will be able to form this is proton removal. Here hydrogen abstraction. The other route is that it can also undergo substitution reaction. For example, you have this compound, it can undergo substitution reaction via SN2 pathway, you will be able to form. These are the common way we can try to perform the reactions. If you see the radical reaction, once you form the radical, you can abstract the hydrogen and you will be able to form the another radical, and which can depends upon the reaction conditions, which can further react with another radical, you get the neutral molecule. Now, let us look at the stability of the radicals, and if you compare this alkyl radical, you have the methyl radical, here you have the dimethyl, here propyl radical, and here again you have the, this should be and this is the tertiary radical. If you see this one, this is the primary radical, this is secondary radical, this is the tertiary radical. The stability of the, look at this one, tertiary radical is more stable comparing to secondary radical, which is more stable comparing to primary radical, which is more stable comparing to methyl radical. This is because you can see here this bond, when you have this bond is much weaker than this in the case of this CH bond, therefore, it can be easily cleaved. This radical can be stabilized as you have the methyl group, and so this is the stability of the radical. And when you compare the stability of the alkyl radical with this allyl benzyl radical, they are more stable. If you see the benzylic hydrogen, this is very weak. It can be easily, if you have the radical, you can easily cleave this bond, you can remove the hydrogen homolytically, you can generate the benzyl radical. This benzyl radical, as you can see here, can be stabilized by the aromatic system by, as you can see here. And similarly, if you have the allyl radical, this also can be stabilized as shown here, you can form the another radical. Therefore, if you compare this allyl or benzylic radical, which are more stable comparing to the alkyl radical, this is because stabilization of the aromatic ring by through delocalization. In other words, if you look at this allylic CH bond, which is much weaker than the alkyl CH bonds, therefore, if you have the radical, it can be readily homolytically cleaved to give the allyl or benzyl radical. And when you compare with this vinyl and alkynyl radical, they are less stable because this bond is stronger than benzylic CH bond. Therefore, and this radical, whatever radical you generate, they are less stable than the alkyl radical. This bond, in other words, this bond is stronger, therefore, and whatever the radical you generate from here, they are less stable than the alkyl radical. The alkyl radical less stable than the aryl radical. In other words, if you see the allyl and benzyl radical, which are more stable than alkyl radical, which are more stable than the vinyl and alkyl radical. These are about the stability of the radicals. In addition to that, if the radical is bonded with carbonyl group, for you have the methyl radical which is bonded with here carbonyl group, here you have the nitrile group, you have here ether group, and again this radical is the carbonyl group. They are more stable. You can see here even the tertiary alkyl radical comparing to this radical, they are more stable because by the electron withdrawing it can exist like this, it can be stabilized by the nitrile group, even you can this ether group can stabilize the radical. Therefore, this radical more stable comparing to the tertiary radical. Whether the functional group is electron withdrawing here nitrile or electron donating, you have the ether group, it clearly irrelevant here, both types seem to be stabilize the radical, both this ether group as well as this electron withdrawing group, this carbonyl group, the nitrile group can stabilize the radical. So, just we have seen about the stability of the radical. Now, let us look at their application in the carbon halogen bond formation. Here an example shown, the reaction of cyclohexane with chlorine in the presence of light. It can lead to the formation of cyclohexyl chloride as a product, where you generate the HCl as a byproduct in this reaction. In the presence of light, it can undergo homolytic cleavage and you will be able to form Cl dot. Once you form this radical can abstract this hydrogen, you will be able to form the cyclohexyl radical, where you generate the HCl as a byproduct. Once you form the cyclohexyl radical, which can react with the chlorine as shown here homolytically to form the cyclohexyl chloride, and you generate the Cl dot. Once you form this Cl dot, which can react together and you can form the chlorine, and alternatively this cyclohexyl radical also can react with the Cl dot, then you will be able to form the cyclohexyl chloride. The first step is known as initiation. You cleave homolytically this chlorine bond and into chlorine radical, and this initiation, once if you initiate the reaction, and then the radical can abstract the hydrogen as shown here, and we form the cyclohexyl radical, and this radical can react with a neutral molecule. Here you have the chlorine, homolytically you can form the another chlorine radical, you have the neutral molecule. This radical now can combine with another Cl dot as shown here, and you make a chlorine neutral molecule. Alternatively, this radical also can react with the cyclohexyl radical as shown here, you form the cyclohexyl chloride as the product. This is known as termination. Two radical can combine together, you form the neutral molecule, and this is known as termination. And this step, the radical reacts with the neutral molecule, you form another radical, a neutral molecule, and this reaction proceeds until you have the substrate. The reaction continues and until you have the substrate. This is known as chain propagation step, and this is known as chain initiation step. That means you initiate the radical formation, you have the neutral molecule. Once if you have this weak bond, this bond can be cleaved in the presence of light or heat to form the radical. That radical once formed, this is known as chain initiation step. Once you form, this is a chain reaction, this radical can now react with the neutral molecule. The reaction continues until you have the substrate. Once the substrate is consumed, the radical whatever you have, two radical can combine together, you form the chlorine, that is known as chain termination step. And this is about the radical reactions. Here the use of light is shown. In the presence of light, chlorine is known to undergo homolytic cleavage to generate the chlorine radical, which can undergo reaction. In this way, if you have the alkane, for example, you can make the cyclohexyl chloride. Already you studied in the newer class earlier, for example, if you have the methane and you can take chlorine in the presence of light, you can convert into chlorinated compound. So, by controlling this chlorine, you can convert completely into CCl4, or you will be able to get a mixture of compound already I have studied. And similarly here shown, if you have the cyclohexane, you can get the cyclohexyl chloride. This all involve a radical pathway. This chlorine is converted into the corresponding radical, which undergoes homolytic cleavage in the presence of light to give the radical. Once with the radical, the reaction can take place, and in this way you will be able to form the corresponding chloro product. Now let us look at, just we have seen, if you have the cyclohexane, the hydrogen can be abstracted using by chlorine radical, and then the reaction can lead to the formation of cyclohexyl chloride. Now let us see here, the reaction of cyclohexene, the allylic CH bond. The beginning, if you remember, and we have seen the allylic CH bond, this very weak bond. If you compare here, this is a weak bond comparing the bond present in the here and the vinyl bond as well as this bond. This is a very weak bond, and now as just we have seen, if you can heat or you can use light here, the use of light shown here, you can also heat bromine, which also can undergo homolytically cleavage to give the Br radical, which can initiate the reaction. You can also use N-bromosuccinamide, this also in the presence of AIBN, and you can form the bromine radical. Now let us look at here, and the reaction of cyclohexene with the bromine, the presence of light is shown, then you will be able to form the allyl bromide. So allylic CH bond undergoes cleavage in this reaction, you form the allylic radical. That radical reacts with the Br dot, then you will be able to form this bromo compound. As just we have seen chain initiation, you have this bond is weak. When you apply light, you can under homolytic cleavage, you form the Br radical. Once you form the radical, as just we have seen, and just I mentioned, this allylic CH bond is much weaker. If you form the radical, this radical can be stabilized by delocalization of the double bond. For example, if you have the radical, you have this one, this you can stabilize by the double bond, you will be able to form this radical. So therefore, and the allylic CH bond undergoes homolytic cleavage, you form this allyl radical. Once you form the allyl radical, this radical can further react with bromine as shown here, and you will be able to form this allyl bromide, and you generate the Br dot. So this is the, as just we have seen the initiation. What you do here first, the bromine in the presence of light, you convert into Br radical by homolytic cleavage of the bromine bond. Once you form the radical, this radical can abstract this allyl hydrogen to form the cyclohexynyl radical. This radical now can react with bromine as shown here homolytically, and you form the cyclohexynyl bromide, and this is as just initiation step. You form the Br radical. Provocation, the Br radical can react, you generate this HBr, then this can further react with the bromine, then you form the cyclohexyl bromide. This is termination step until the substrate have the reaction proceeds. Once the substrate is consumed, then this Br dot can react with another Br dot, there you form the bromine back, and similarly you can also bromine radical can react with this one. If you have this one, then in this way you will be able to terminate the radical reaction. So just we have seen two examples. First example involves chlorination of cyclohexane. You have the alkane, you can convert into cyclohexyl chloride by photochemically. You can convert in the chlorine into radical, which can abstract the hydrogen. You can convert into cyclohexyl chloride. Then we have seen the allylic halogenation. If you have the allylic CH bond, which can be radically reacted with the bromine, the presence of light, you can get the cyclohexynyl bromide. We have seen the one example. Now let us look at another example. Here you have the silver carboxylate you have, and when you react with the bromine, the in CCl4 solvent, you will be able to form the alkyl bromide. You have the carboxylate, and in this reaction you lose carbon dioxide and silver bromide. The mechanism shown here, when you have the silver carboxylate with bromine, you can form this intermediate. You form the silver bromide and plus this. Once you form this one, which can undergo cleavage, and you will form this radical and Br dot. Once you form this radical, this can lose carbon dioxide neutral molecule, you form the alkyl radical. This undergoes decarboxylation to give this alkyl radical. This radical can further react with the substrate here. You can react with this radical now can react with this one, then you will be able to form this alkyl bromide. You form this radical now can lose carbon dioxide, you will be able to form another radical. So, the reaction proceeds like this until you have the substrate. This is known as Hunsdaker-Borodin reaction. If you have the silver carboxylate and you can try to react with the bromine in CCl4, then you will be able to form the alkyl bromide via decarboxylation. Is a very useful reaction. In this, you lose carbon dioxide as a byproduct. Now, let us look at another example for the carbon halogen bond formation. Here the reaction of alkene is shown. So, if you remember earlier we have seen, if you have the cyclohexene and if you have the bromine, in the presence of light you can convert into cyclohexenyl bromide by the abstraction of allylic hydrogen. You can form the allylic radical which can react with bromine, you get the cyclohexenyl bromide. But now let us look at here, you have the alkene. In this, when you react this alkene, this tribromomethane, and in the presence of peroxide, dibenzyl peroxide, which when you heat it can undergo homolytic cleavage to give this radical. So, in the presence of this dibenzyl peroxide and this alkene readily undergoes reaction with this one, then you will be able to get this derivative. The reaction mechanism shown here, as just I mentioned, when you heat this one it can undergo homolytic cleavage, since this bond is very weak, and you will be able to get this radical. Once you form this radical can abstract this hydrogen, and you will be able to form here benzoic acid in this case, and you generate this radical. This radical can undergo addition reaction with the alkene, and you will be able to get the secondary radical. Once you form this radical now can abstract the hydrogen from this tribromomethane as shown here. You get this addition product where you generate this radical. This radical, as just we have seen, again can undergo addition reaction with alkene, and you form the secondary radical. The secondary radical can go like this until you have the substrate. This is another example here. In the previous case we have seen the allylic CH bond undergoes bromination, you get the allyl bromide, whereas in this case this radical, whatever this radical you generate, this radical undergoes addition reaction with the alkene, and you get the secondary radical, alkyl radical. That alkyl radical abstract the hydrogen from the dibromomethane, which can lead to the formation of a radical and a neutral molecule addition product. In this way you will be able to do the addition reaction using radical species. Now, let us look at another example here. This also for the carbon halogen bond formation. In this reaction, when you take this organomercury compound, you have this, when you react, you have here this side you have two different substituents. When you react with this compound in CCl4, and you will be able to get a alkene as is shown here. This one undergoes halogenation, and you get this alkyl chloride where you generate chloroform as the byproduct, and you can see the reaction mechanism shown here in this case. And when you have the carbon tetrachloride, it can undergo homolytic cleavage. You generate this radical. Once you form this radical now can react with your substrate as shown here, and you will be able to form this, abstract this hydrogen, you form this tertiary radical where you generate the chloroform as the product. Once you form the tertiary radical, this tertiary radical can now convert into alkene, isobutene, and you generate this radical. This radical now undergoes homolytic cleavage. Further, you form the alkyl radical, you produce mercury, and this alkyl radical now can further react with the carbon tetrachloride and you will be able to form the alkyl chloride. You generate the this radical. This radical now can further react as shown here. In this way, if you have this organo mercury derivative, which can be, since you have the hydrogen, this hydrogen can be abstracted by the radical that you generate from the carbon tetrachloride. In this way, the reaction can be initiated, and in this way you can convert into, if you have this, you can make this alkyl halide as the chloride as the product. So, this reaction can be carried out in the presence of light as well as heating, and if you have the carbon tetrachloride, or you can also add radical initiator. In this way you form the radical. Once if you form the radical, the reaction can be facilitated, and you can see here in this way you can make the alkyl chloride as the product. So, another example from the literature. Now, let us take this carboxylic acid. This carboxylic acid in the presence of iodobenzene diacetate and iodine in carbon tetrachloride, when you heat, it undergoes halogenation. You can make the alkyl iodide as the product. It undergoes decarboxylation followed by carbon iodine bond here, and the mechanism of this transformation shown. When you have the carboxylic acid, when you react with iodobenzene diacetate, and you will lose 2 molecules of acetic acid, where you make this hypervalent iodine reagent. Once you form this one, this reagent can react with iodine as shown here, and you will be able to form this derivative. This derivative can undergo cleavage now as shown, can undergo homolytic cleavage. You form this radical. Once if you have this one, this can lose carbon dioxide, and you have the alkyl radical. This alkyl radical can react with the iron radical. In this way you can make a carbon iodine bond. So, for example, here the reaction of this steroid having carboxylic acid can be converted into alkyl iodide as the product using the hypervalent iodine reagent. Here this is commercially available. Once if you have this iodobenzene diacetate, you can try to react with the carboxylic acid, the substrate, you form this intermediate, the substrate reacts. Once you form this one, when you add iodine, it can be readily converted into this corresponding alkyl iodide as the product. Here another example shown, the formation of carbon-carbon bond. So far we have seen the several methods for the formation of carbon halogen bond. Now let us look at some examples for the carbon-carbon bond formation via radical pathway. Here, as just we have seen, here you have the hypervalent iodine, which can be readily reacted with this sulfonyl derivative, and in the presence of cyclohexadiene and under irradiation in dichloramethane room temperature, you will be able to form a carbon-carbon bond. The mechanism of this reaction shown, this hypervalent iodine reagent, as just we have seen, the prism light can undergo cleavage, and you will be able to form a radical as shown here, and you will be able to form this radical, and you lose carbon dioxide, you make this alkyl radical. Once you form the alkyl radical, which has this alkene is bonded with electron withdrawing group, sulfonyl group, which can now undergo addition reaction, and you form this radical. Once you have this radical can abstract hydrogen from this cyclohexadiene, so you can get this addition product, and you have the cyclohexadienyl radical. This radical can now react with this radical, and it can abstract hydrogen from here, and in this way you will be able to form benzene, and you generate this intermediate. Once you form this one, this can now convert into, you can see the carboxylic acid, iodobenzene. So, in this way, for example, if you have the alkene which is bonded with the electron withdrawing group, if you have the radical which can be readily added to give the addition product, as you can see here, you can make a carbon carbon bond via radical pathway. Here another example shown. Here the reaction of quinoline shown, it can react with the THF, the presence of iodobenzene diacetate, and sodium azide to give this compound. In this, as you can see here, just we have seen this iodobenzene diacetate can react with the N3 minus nucleophilic substitution. You can form this intermediate. Once you form this one, this now can convert into, you can see here, as a radical, azide radical. Once you form this radical abstract this hydrogen, you form this radical, which radical, this radical can be stabilized by this oxygen. Once you form this radical, this radical now can couple with this quinoline derivative as shown here, and in this way you can make a carbon carbon bond. In this case, the quinoline can be coupled with this tetrahydrofuran, and in this way you can make a new carbon carbon bond. This azide anion is oxidized to azide radical, you can see here, and abstraction of electron rich hydrogen atom for the formation of carbon centered radical. So, hydrogen atom abstraction takes place from here, and you generate the carbon centered radical. So, this radical now formation of alkylated product through carbon centered radical. This radical can undergoes alkylation. In this way you will be able to form a carbon carbon bond. So far we have seen some example for the carbon carbon bond formation through radical pathway. Now let us look at some more example. Here the reaction of acrylonitrile with this alkyl iodide is shown in the presence of tributyl tin hydride and AIBN. So, this when you AIBN readily undergo cleavage to give the this radical, this is a radical initiator. Once you form this one, this radical now can react abstract the hydrogen from the tin, then you will be able to form the tin radical. Once you form the tributyl tin radical, this if you have the alkyl halide, for example, it can react. You form tributyl tin halide plus alkyl radical. This radical can undergo addition reaction. For example, if you have the alkene which is bonded with electron withdrawing group, electrophilic in nature, it can undergo addition reaction. You have the second radical. That radical can be further reacted with the tributyl tin hydride, you get the addition product. So, when you use the AIBN shown, this is a structure of the AIBN, it can undergo cleavage to form this radical, and you lose nitrogen molecule. Once you form the radical, Now, this radical can react with this one and you will be able to form the tributyl tin radical shown here. So, the tributyl tin radical can now react with this alkyl iodide as shown here, and you form a tin iodine bond which is stronger than tin hydrogen bond. That is responsible for the cleavage of this one. You form the alkyl radical. Once you form the alkyl radical which can undergo addition reaction as shown here, and you form the alkyl radical which is stabilized by the nitrile group. Once you have this radical can react with tributyl tin hydride as shown here, and you will be able to get the addition product. For example, if you have the alkyl halide, you can make the corresponding nitrile by addition reaction. For example, in this case you have the acrylonitrile, it can be readily reacted, you can get this alkyl nitrile as the product. Here another example shown, as just we have seen the earlier case, we have seen the intermolecular reaction. You have the alkyl iodide and acrylonitrile which can undergo addition reaction in the presence of tributyl tin hydride and AIBN. AIBN is the radical initiator, and it can react with the tributyl tin hydride. You form the tributyl tin radical which can undergo reaction. Then here shown the reaction with this ester. You have the earlier we have seen the nitrile group, here you have the ester group. So, basically this is the methyl acrylate which can intramolecularly undergo cyclization. You will be able to get this addition product as just we have seen, and in the presence of this ABN, tributyl tin hydride can undergo reaction. This radical can be stabilized by the nitrile group. Once we have this one, this can, as just we have seen, it can give the tin radical. This radical, when you have the substrate, this can readily react. For example, in this case you have the alkyl bromide which can react. You form the tributyl tin bromide plus alkyl radical. In this case you form the tertiary radical. Once you form the tertiary radical which can undergo addition reaction intramolecularly, and you will be able to form if you have the radical, so there is two possibility. If the radical undergoes addition here, I think here one carbon is less, and it can undergo addition reaction here, then you will be able to form a 5-membered ring. You form this radical. So, this radical, once we have this one, this can further react with tributyl tin hydride. In this way you will be able to get this product. So, this is an example for intramolecular reactions. Here you can have the ester or nitrile group, and which can be readily reacted, the radical can undergo addition reaction. You form the radical here, that radical can further react with the tributyl tin hydride. In this way you will be able to get this addition product. Here another interesting example is shown, is a tandem reaction, as just we have seen, and if you have the tributyl tin radical that can be generated from tributyl tin hydride and AIBN. this radical can react and you form this tertiary radical. You have this radical. Once we have this radical, you can see here, and this radical can undergo addition reaction, you form this. Since you form the 5-membered ring, so you form this radical. This secondary radical can react with this alkyne to give this radical, the vinyl radical, when you react further with tributyl tin hydride, abstract this hydrogen, then you will be able to get this compound. The stereochemistry you can see here, since you make the 5-membered ring and it should be syn, you can see here, and here the cyclization takes place. What you do here, you make a tandem cyclization, you make a tricyclic compound where you make a 2 carbon-carbon bond, and with the exocyclic methylene group. You can see here the radical reaction find wide applications. For example, if you have this kind of substrate which can be cyclized through tandem pathway, then you will be able to get this stereospecifically this tricyclic scaffold. Now, let us look at CO trapping and the carbon-carbon bond formation. Now, here you can see here you have the alkyl iodide, as we have seen just now. When you have the alkyl iodide which can be reacted with this alkene and the presence of AIBN, and here the reaction also has been carried out in the presence of carbon monoxide, and this is a 3 component reaction. They can undergo reaction, you will be able to get this keto compound. As we have seen, the AIBN can initiate the reaction and it can form the radical when the reaction has been carried out in benzene at 80 degrees Celsius. As just we have seen, when you have the AIBN and this allyl tin reagent, you have AIBN can convert into this radical. This radical now can convert into homolytic cleavage of this, can give this alkyl radical. Once you form this alkyl radical, this can undergo addition reaction. Just we have seen 2 examples. One, we have seen the addition to the acrylonitrile, another one is methyl acrylate, and similarly you have the which can undergo reaction this carbon monoxide, and you will be able to form this radical. Once you form this radical, and this radical can undergo addition reaction with this alkene as shown here, and then you get the tertiary radical. This radical can now convert into neutral molecule, and what happens here, the carbon tin bond undergoes homolytic cleavage in this case, and you get this radical now can react. If you have the alkyl iodide, it can further react and you form the alkyl radical and tributyl tin iodide. In this way the reaction can be carried out. So, if you have the alkyl halide, you can do the carbonylation as shown here, and it can undergo addition reaction with carbon monoxide and you get the carbonyl radical. Once you have the carbonyl radical which can readily undergo reaction with this alkene, and you form the tertiary radical which can lead to homolytic cleavage of the carbon tin bond, which is very weak bond which can undergo cleavage. You will be able to form a carbon iodine bond which is stronger than this carbon tin bond. It can lead to the homolytic cleavage. In this way you will be able to form this carbonyl derivative as the product. Now, let us look at, just we have seen the reaction to alkene allyl tin reagent, and now let us look at another example here. You have the alkyl iodide and carbon monoxide. Here also you have the allyl tin and acrylonitrile. So, the earlier one we have seen the 3 component reaction. You have the alkyl iodide and allyl tin with the carbon monoxide which can lead to the formation of carbonyl compound, a keto derivative. Now, let us look at this reaction in the presence of A, B, and as we have seen, and you can generate the radical, then radical can react this alkyl iodide into the alkyl radical. As just we have seen, this radical can undergo addition reaction with carbon monoxide, you get the carbonyl radical. This radical, as just we have seen, and it can undergo addition reaction with acrylonitrile, you form this radical, secondary radical. This radical can be stabilized by the nitrile group. Once you form this radical can undergo addition with this allyl tin as shown here, the double bond. You form this tertiary radical. Once you form this tertiary radical, as just we have seen, and it can undergo homolytic cleavage as shown here, and what you do here is generate the tributyl tin radical and neutral molecule here, and this, once you form this radical, this can further react with alkyl iodide to form the alkyl radical. The reaction continues until you have the substrate. In this way, for example, you can use the radical reaction. For example, here alkyl iodide can be coupled with acrylonitrile carbon monoxide allyl tin to give highly functional molecule. You have here double bond, you have the nitrile group, and you have also carbonyl group, and its 4 component can be coupled using this radical reaction, and you will be able to make multiple carbon-carbon bonds. Here you make a carbon-carbon bond between this alkyl halide and carbonyl group. You also make another bond between this carbonyl group and this vinyl tin, and this, in this way you can make a multiple carbon-carbon bond using the radical reaction. So, another interesting example shown, just we have seen the reaction with alkyl iodide, carbon monoxide, acrylonitrile and allyl tin, and in the place of acrylonitrile here you have given this alkyl ester derivative. This also can be coupled under similar conditions to give this coupled product. As we have seen, you form the alkyl radical. This alkyl radical can react with the carbon monoxide. You can get this carbonyl radical. This carbonyl radical can now undergo addition reaction. In this case, you can see here it leads to addition with this triple bond. You form this radical. Once you form this radical, this, as just we have seen, it can react with this allyl tin reagent as shown here. You will be able to form once you form this radical, it can undergo homolytic cleavage, and you will be able to form as the product. So, this also another example, and if you have the alkyl halide, you can try to couple with the carbon monoxide this alkynyl ester and allyl tin by the presence of AIBN, then you will be able to make a multiple carbon carbon bond. You can get this highly functionalized molecule. As you can see here, the reaction is stereoselective. And here the reaction of this alkene, carbon monoxide and silyl hydride is shown here in the presence of AIBN. As just we have seen, AIBN can convert into radical when you heat it, radical which the radical can now abstract the hydrogen from the silyl hydride. You form this radical, silyl radical. The silyl radical can undergo addition reaction. Since you use the bulkier silyl radical which undergoes reaction selectively, this less substituted double bond, you get this secondary radical. Once you have the secondary radical, as we have seen, it can undergo addition reaction with the carbon monoxide, you get the carbonyl radical. Once you have the carbonyl radical, it undergoes intramolecular cyclization with this double bond to give a tertiary radical. You can see here, you can make a 5-membered ketone like this. Once you form the tertiary radical, this radical can react with the silyl hydride as shown here homolytically. You can convert into the product. You form this in this way silyl radical. This silyl radical can further undergo addition reaction. So, if you have the double bond, so chemoselectively you can, the less substituted double bond can be, since you use a bulkier radical, selectively can undergo addition reaction and you will be able to have this radical. This can undergo addition reaction with the carbon monoxide that can lead to the cyclization. In this way you will be able to get the cycloketone as the product. Here another example shown here, this is the coupling of this beta keto ester with this alkene and the carbon monoxide, the presence of manganese acetate, acetic acid under heating, and you will be able to form this cyclic lactone as the product. You can, the reaction mechanism shown when you have the manganese 3 and it can be converted into, you form the radical. This can form the when you heat it, it can undergo cleavage. In this way you will be able to form the radical. Once you form this radical can now, since you have the alkene, it can undergo addition reaction. You have the secondary radical. This radical now can react with the carbon monoxide. Addition reaction, you get the carbonyl radical. Once you have the carbonyl radical, and this radical now can convert into this. Once if you have this one, now this can be reacted, as you can get the carboxylic acid. Once you have the carboxylic acid, you have the manganese 3 which can now again form the radical as just we have seen. This radical and this radical can undergo now cyclization here as shown here, and you form this one and radical cyclization. In this way you will be able to get this lactone as the product. This is well known in the literature. When you have the beta keto ester and this condition acetic acid and then manganese acetate, you can form the radical, and this radical can be further utilized for the addition reaction. What you do here, first you do addition with alkene followed by then carbon monoxide, you get this radical, and once you have this intermediate which can further, you have the another CH bond, you can be converted into, in the presence of manganese 3 to the radical. This radical can undergo further reaction with this one. In this way you will be able to make this lactone as the product via radical pathway. Here another example shown. If you look at the previous one and this one, we do not use here AIBN as a radical initiator, and in this case the reaction of alcohol with the carbon monoxide, the presence of lead tetrastate is shown under heating in benzene solver can lead to the formation of this lactone. So, when you have the alcohol, when you react with the lead tetrastate, you will be able to form this compound. You lose acetic acid. So, you gave the form this one. Once you have this can undergo homolytic cleavage under heating, and you can form the radical. This radical now can abstract this hydrogen as shown here. You will form this one. So, the delta hydrogen. So, you will form this secondary radical. Once you form this radical when you have the carbon monoxide can undergo addition reaction as we have seen earlier. You get this carbonyl radical. This carbonyl radical now can as shown here, and you have the can undergo cyclization as shown here. In this way you will be able to form the lactone. For example, if you have the alcohol and if you have the aliphatic alcohol, and you can try to readily react with the carbon monoxide in the presence of lead acetate, and you can try to, for example, primary and secondary alcohol having delta hydrogen atom are better suited for this method. You can try to cyclize, you can make the lactone as the product. Here another example shown here. Here the reaction of ketone with the carbon monoxide in the presence of ferrous sulfate and hydrogen peroxide is shown here. And as we have seen, and you can form the radical, the ferrous sulfate hydrogen peroxide, which can undergo addition reaction, and you get this compound. Once you have this one, now this can undergo cleavage here, and then you form this radical, and this can undergo cleavage, and you will be able to form this radical. Once you have the radical, this radical can now undergo addition reaction with the carbon monoxide. As we have seen, you get the carbonyl radical. Once you have the carbonyl radical, and you have the, it can be oxidized to this acetylene cation. Once we have this one, this can be reacted with the hydroxide ion. In this way you will be able to get this dicarboxylic acid. For example, if you have the cyclohexanone in the presence of ferrous sulfate and hydrogen peroxide and carbon monoxide, you can get this dicarboxylic acid product through radical pathway as is shown here. This is a crucial step. Once you form this radical, it can be further oxidized to this acetylene cation, where this Fe3 can be reduced to Fe2. Once if you have this one, this can be reacted with the hydroxide ion, you can get this dicarboxylic acid as the product. In summary, so in this lecture we have seen the principles of the formation of radical and their application for the carbon halogen carbon carbon bond formation. Radicals can be generated by three ways. If you have the weak bond, for example, if you have the peroxide or for example chlorine or bromine, they can be easily cleaved into radical. This can be carried out thermally or photochemically. You can also generate the radical by giving electron by redox process. So, three ways you will be able to generate the radical. This radical is very reactive, except few radical, most of them are not stable. We also have seen the stability of the radical. If you compare the stability of the alkyl radical with allyl benzyl radical, the latter are more stable due to the delocalization with this double bond or aromatic ring. So, this radical can be readily reacted with substrates. We have seen one example. If you have the alkane, cyclohexane and chlorine, in the presence of light you can convert into cyclohexyl chloride via radical pathway, which is very useful reaction. The second example we have seen, you can also abstract the allylic hydrogen, which is very weak bond. For example, if you have cyclohexene, you can try to react with bromine in the presence of light, you can get cyclohexyl bromide. Then we have seen some of the examples. You can also try to react radical. You can also try to produce radical in the presence of radical initiator. For example, if you have the peroxides, you can heat you can form cleave the oxygen oxygen bond can undergo homolytic cleavage to give the radical which can be used as the initiator. Then we also have seen several examples where we use AIBN as a radical initiator, which are known to undergo cleavage to give the radical. That radical can be further reacted with the substrate to initiate the reaction. We have seen the combination of AIBN, tributyl tin hydride, which can be readily used for the, if you have alkyl halide, you can try to make the alkyl radical using these reaction condition tributyl tin hydride and AIBN. Once we form the alkyl radical, we have seen the several examples. It can be added to alkene, or if you have the carbon monoxide, we have also seen some examples for multi-component coupling. It can be reacted with the carbon monoxide, you get the carbonyl radical which can be further reacted. As you can see, then you can see it has broad applications. Stereoselectively you can carry out the reaction. Later we also have seen some examples where you do not need the radical initiator. For example, if you have the manganese acetate, if you have the beta keto ester, you can generate the radical under heating in acetic acid medium. You can generate the radical. That radical can be further utilized for the addition reaction. Then we also have seen example, if you have the alcohol and if you have the lead tetrastate, you can try to readily generate the radical. You can make this alkoxy radical which can be further utilized for the applications. Then also we have seen the transformation of cyclohexanone to dicarboxylic acid in the presence of carbon monoxide using ferrous sulfate and hydrogen peroxide. This also involves a radical pathway. If you look at all these reactions, they find broad utilities in the synthetic chemistry. Therefore, radical reactions like other reactions can also be utilized. We also have seen one example, for example, you can also use for tandem cyclization. In this way, you will be able to make polycyclic compound. You can, in other words, you can make multiple carbon-carbon bonds, and that can be carried out using the radical reactions. With this, we conclude this lecture. Thank you very much.